Welcome back. In the last lesson, we started with looking at power, and power is defined as the rate of change of transfer or transformation of energy. And as we know, so here is the change of energy per time, so that makes it a rate of change of energy. The rate of change of energy in transferring and transforming energy is known as work. So the power formula for yesterday is delta E on T, or we could be just using W on T. Now, that's a great formula to use when we know that we are changing our velocity or we're changing our position in space. So if we were to lose or gain kinetic energy, so delta K, then we use this formula. If we are driving a car, however, so let's have a look at our car down here, and we are driving it forward. The way that we work it, we make a car go forward is we press the accelerator pedal in the car. Now this makes the engine move the car forward with a driving force. But and that would mean that there is an unbalanced force, so the car would now accelerate forward. But we know from driving cars that if you press the accelerator down, yes, it will get going and it will start accelerating, but even though you are pressing it down at a certain level, it won't get any faster. And this is the reason. The reason is that there is frictional force acting back. When the frictional force and the driving force become the same, the car then travels down the road at a constant velocity. And if we want to get faster again, I have to press the accelerator even further towards the floor, and that would make the driving force get bigger, and eventually the frictional force would get bigger, and I would get to another point of constant velocity. So when we are doing some systems, friction becomes a major problem. That even though I am traveling and I am doing work, I'm actually putting energy into this system here, but chemical energy is being converted into the driving force, into the energy that makes this driving force happen over here. I am not accelerating, I'm getting constant velocity. So sometimes we must take friction into account, and friction can cause a constant velocity. So what will happen here is we can't use our delta K. If we use delta K, we know that this would be a half mv squared minus u squared, and the final velocity and the initial velocities will be the same velocity, because even though I'm putting energy into the system, my initial velocity might be 20 meters per second. I'm still putting energy in, but because of the friction force, my final velocity is still 20 meters per second. So even though we have energy going in, there is no change in velocity. So this formula can't be used. So how do we cope with power when our velocity is not changing? So let's have a look at this here. This is the formula that we're using. Power is work divided by time. And we know that work is given as work, the formula for work is Fs. It's a force moving an object through a distance. So just replacing this in this formula with Fs, we get the following expression. If we were then to separate, then we have that F times S on T, we recognize that S on T is velocity equals displacement over time. And this is true when my velocity is constant. So velocity is displacement over time. So that means that we can replace this with V. So this formula here that we're about to use can be used to determine the power of a system where a force is acting, but the velocity remains unaccelerated. So that means that the velocity remains constant. So let's have a look at our diagram here. This is from your textbook. We've got a person pushing a box. Okay, so if a person pushes a box with 40 newtons, we have an unbalanced force. Therefore, this box should accelerate forward. But what we're saying here is this box is traveling only at 1.5 meters per second forward. And we call this an average speed because obviously it might just speed up or slow down a little bit because not all of us are great and we're not machines. So it's got an average speed. We'll just say it's a constant speed going forward of 1.5 meters per second. But shouldn't an unbalanced force give a accelerating velocity? Yes, it should. Why isn't it? The reason being is that there is friction acting backward here, and this friction here and this driving force here that he's pushing on are now equal. Once the object gets going, those two forces become equal, and therefore the velocity does not accelerate. It just maintains the velocity that it had prior to this friction becoming the same as this driving force. So now we can work out what is the amount of power that is exerted on this box. So we're going to use this formula now because we recognize that we have a force acting with a constant velocity. So power would equal the force, it's 40 newtons that is applying, times 1.5, which is the average velocity, and that will become 60 watts. Okay, so we apply this formula where a force is acting and it's giving rise to a constant velocity. In other words, this takes into account that there is friction in the system acting backward against the driving force. But sometimes we don't push in, let's just go back to that last one here. We've got this fellow pushing in this direction and the velocity is in the same direction. The two arrows, two vectors there are in the same plane, in the same direction. This fellow here is pushing a mower and he is pushing down through the handles of that mower, but the actual mower is moving forward at 0.8 meters per second. So we have a force, the force is at this direction and the velocity is in another direction. And so this is where these two do not coincide. So we go back to our formula. Our formula says that P equals F times S. I'm now going to modify the formula and put the parallel symbol there because we know that work is done, Fs, work equals Fs, and work is only done by the force that is parallel to the displacement there. And I have just realized I've written this thing over here incorrectly, so I'll go back. If you are copying that down, please correct it. It's meant to be FV, as we know. Okay, so power is force parallel to the velocity. So in this case here, let's have a look at what this fellow is doing. Though there is the force going down here, we're going to now take that force, okay, and we are going to divide it into its two components, the vertical component and the horizontal component here. So that's 30 newtons there, and we have an angle here of 20 degrees. This means that this one over here would be 30 cos 20, and this would be 30 sine 20. So which of these two, the orange arrow or the brown arrow, which of these is parallel to our velocity vector? Well, the velocity vector is going this direction, so it's this one here. It is the 30 cos 20. So we can now calculate the power. The power that this gentleman is generating into the mower, or producing into the mower, is the force, and the force is 30 cos 20, times the velocity in the parallel direction, which is 0.8. So taking our calculator now, we can calculate this. So that's 30 cos 20 and multiplying by 0.8, we get 22.6 watts going on. Right. Okay, so there is a worksheet that is now required to be done, which will take you through using this formula. So that you can use a simple formula, which is P equals FV, and this one here is where you automatically have the two vectors in parallel, and you can use P equals F parallel to V when we know that the force is not in the same direction exactly as the velocity, and therefore we have to resolve the vectors into its two components. Okay, there will be work solutions for you to help you along.